Jai Hind everyone. So this is Dr. Avdhesh Gupta, professor in Ajay Kumar Garg Engineering College. So the subject computer networks, it belongs to BTech third year students, 6th semester students. So today's topic is data and signals. So let's start. Data and signals. In the previous lecture, we have already discussed what is data and what are the different types of signals. Now, let's focus on the various types of transmission impairment. So, what are transmission impairment? Transmission impairments are the something like noise or something additional signals that has been added or that has been removed from the existing signals. If the signal, some additional signal has been added to your existing signal, it is called as noise. If some power of your signal has been lost, then it is treated as the loss in the signal. Okay, so we can understand these types of impairment by these three topics: attenuation, distortion, and noise. So, what is attenuation, what is distortion, and what is noise? Focus on these 3 points. These 3 points are very important topics for your preparation in computer network subject as well as for your future if you want to study further. So, what is attenuation? In attenuation, the power of a signal has been lost, some power of signal. So, if the power of signal is this, after the loss in the power of signal, it lost some power and the signal shape is this. Then we can amplify the power of signal to the previous one. So, this is attenuation. Means what? If the power of a signal has been lost or has been decreased some power, obviously, like in electricity, you receive some lower voltage of signals, it means the power of electricity has been lost somewhere. So, you need to use a stabilizer to boost up its signal. So, here we can use amplifier. Amplifier amplifies or amplify boost the power of signals. So, this signal power has been converted to this signal power. So, signal power has been boosted up or signal power has been recovered as the original. So, this is attenuation. So, in attenuation, the power of signal has been lost. So, how we can study this? Suppose a signal travel through a transmission medium wired or wireless, and its power is reduced to 50%, one half. Okay, let's say in starting it's P1, and then when it reaches to its destination, it means P2, the signal power becomes half, P1 upon 2. Its power reduced to one half. It means that P2 is 1 by 2 P1. So, in this case, attenuation or the loss of power can be calculated as this. This is the formula: 10 log 10 base 10 P2 upon P1. It means 10 log base 10 P2 upon P1. It means P2 is equals to P1 upon 2 and upon P1. So, it means 0.5 P1 upon P1. It means 10 log 10, 0.5, or you can say minus 3 decibel. So, understand it. If the power loss is just half, but a loss of 3 decibel is if we lose the signal power just 50%, but we lose 3 decibel of the signal strength. Okay. Now, next case, if the signal power increased 10 times by using an amplifier, if the signal power increase, what will happen? Then using the same formula, 10 log 10, 10 P1 upon P1, then it becomes 10 decibel. Think about it. If we lose just a 50%, then we lose 3 decibel. But if increase 10 times, then it's 10 decibel only. So, losing the signal is more effective, is more dangerous. So, because we cannot listen, we cannot identify what type of signal we are receiving. there is some loss of signals, loss in energy. So we are not able to read, or we are not able to view that particular signal. That's why we need some amplifier in the existing signal so that we can recover the power of signal. But if we increase the 10 times, so only 10 times. Okay. So next one is distortion. What is distortion? This is another dangerous thing. Like you seen that in attenuation, the power of signal has been decreased, but in distortion, the overall signal has been disturbed. Like for example, this is a type of composite signal. You have already studied that the signal and the composite signal. Composite signal is a type of signal where we are using, suppose this is a signal. So at this point, another signal is already there. So it means this is composite signal. It comprises two different signals. The high and lower node is there, but at a high and at the lower node, there are another type of signal is there. So it is a composite signal. So if we read this signal, so this is the high node and this is the lower node signals at this point. What happened at the other end when the signal has been received? Then see this shape. See this shape and see this shape. So the shape of signal has been disturbed. So whatever you are sending to me, I am not able to receive the data as you are sending. It is not same. It is disturbed. So distortion is very harmful for us. Harmful, it means it is not beneficial to receive some distorted signal. We cannot recover it by using some simple medium. Okay. Another type of this is attenuation. What is attenuation? Like you have seen that in attenuation, the power of signal has been lost. In distortion, the shape of signal has been changed. But in noise, some additional power of signal has been added to your existing signal. Like for example, if you are listening my voice, you are also able to listen the fan voice also, the AC voice also. So it means this particular voice has been added with my voice. So what will happen? This is a transmitted signal, original signal. This is the atmospheric noise that has been added to your transmitted signal. So what will the shape? This will be the shape of transmitted signal. So what will happen? This noise has been added to your existing signal and the shape of your signal has been changed something, not exactly distorted, not distorted, but has been added something. Means what? This is the peak point. So here this is the peak point. This is the peak point, this is the peak point. These are the peak points. Either loss or up and down are there, not exactly same. So this is noise. So to study the noise, to understand the noise or different types of numerical, we are just discussing some numerical examples that is very important for your exam preparation. That is, if the power of a signal is 10 milliwatt and the power of noise is 1 milliwatt, micron watt, or you can say, what are the value of SNR? SNR is the signal to noise ratio. Signal to noise ratio and SNR dB. If signal to noise ratio can be calculated in decibel, then what can be? So just SNR is equals to 10,000 mu W upon 1 MW. Okay. So which is equals to the 10,000. So SNR dB is equal to 10 log 10, 10,000. It means 10 log 10, 10 to the power 4 or 40. It means if we are calculating SNR into SNR dB, so it is equals to the 40 decibel. Otherwise, it is equals to SNR is equal to 10,000. So how can you calculate SNR? SNR can be calculated as this particular noise power upon signal power. Noise power upon signal power is equals to the SNR. Okay, sorry. signal power upon noise power. The value of SNR and SNR dB for a noiseless channel. If there is no noise, then what will be the SNR? If there is no noise, then noise signal is a 0. So signal power upon noise power, noise is 0. So SNR becomes infinite. Similarly, SNR dB is also infinite. So can you assume that any signal that you are receiving that is without noise? I think no. In digital signal, can you imagine that any digital signal that you are receiving is without any noise? Feasibly, it is not possible, because some type of noise, like for example, this is a video we are creating. So there are moisture, there are some air, that medium contains some another thing. So maybe you are not seeing this particular moisture or anything else, but there exists something. So it means, similarly, if my voice is coming to you, some additional voice has been added. So it means we cannot assume that any signal that through any transmission medium is noiseless. So the noise has been added. Maybe the noise, there is no need to remove the noise, as the signal is too sharp and signal strength is too good, and we are receiving the signal with noise, and we can assume that this is the original signal and there is no noise, because the signal power is too high and the noise is too low. Noise power is too low, but cannot become 0. Okay. So we can write here also, we can never achieve this ratio in the real life. It is an ideal case. Okay. Because it is infinite. SNR is infinite. So two cases are there, a high SNR and the low SNR. What will happen if their SNR is high? When SNR is high? SNR is high when there is signal power is high, noise is low. SNR is low when the noise power is high and signal power may become low, or the SNR is just equals to the signal power, or noise power is equal to the signal power, or noise power is greater than signal power. So this is the large SNR. This is a signal power, the high signal power, but noise is very low. So what will happen? This type of signal plus noise. So the strength, maybe this can be understood by distortion. This is the example of distortion also, because this noise has been added to this signal and the distortion happens. This is the distortion. Yes, this is distortion, because what is the reason behind distortion? Distortion means just simply change the signal shape. But what is the reason behind distortion? Maybe some noise. Okay, maybe some other reasons also. So another thing. So in this scenario, you can observe very easily that the shape of signal has been changed, but the power of signal remains same, because there is very little impact of the noise on the signal. But in next case, where signal power is low and noise power is high, then what will happen? The overall signal shape has been changed, and now this signal is tough to identify that what is the original signal, because we are listening some additional, some equivalent, or some more than the actual signal. The noise is there. So this is not easy to recognize the actual signal. Okay. So these are the two cases. So data rate limit. A very important consideration in data communication in networks, how fast we are sending the data to another end. It's basically depend on the power or bandwidth of the cable. Like for example, we are assuming that nowadays we are using 6G, so we can say that 100 Mbps or 1 Gbps. So basically the bandwidth available. The bandwidth available for the different types of communication channel is not same. If you are using Cat5 or Cat6 cable, Cat5 cable supports 100 Mbps bandwidth and Cat6 cable support 1 Gbps data bandwidth. Similarly, optical fiber cable supports 1 terabyte also, but in other it is low. So Even in Wi-Fi signal, some router or some repeated devices supports 1 GB bandwidth of Gbps, and some supports 100 Mbps also. So bandwidth plays a very important role to decide data rate limit. Next is the rate of the signal we are using. This is very important topic. The rate level of signal. We can send the data, we can send the digital signal, but there is certain levels, 1, 2, 3, 4, 5, 6 level. 6 level of digital signal we can send through a single signal. The third one is the quality of channel, that is level of noise. So there are two topics, noiseless and noisy channel. So we will study along with these three points. So increasing the level of a signal may reduce the reliability of the signal. So this one, the level of signal. What will happen if this is a signal? So what do you think that this is 1, this is, let's say, this is 0, this is again 1, or 1 plus 1? What? If we measure this, so it means this is level 2, this is level 1. So it means we can send two different signal along with one signal along through the communication channel. We can transfer two levels. So if we are sending multiple levels, 1, 2, 3, 4, 5, 6 levels. So what can you imagine that this type of signal we can send? No. The reliability of the signal is reduced. We can send one signal, two signal, 4 signal. Yes, you can send, but it depends on the available bandwidth also. But if we are increasing it exponentially, then obviously the level of signal, if we are increasing level of signal, it reduces the reliability of the signal. So let's take another example. The Nyquist bit rate algorithm. Yes, there is a formula for Nyquist theorem. Okay, we will check this formula in next slide. So, does the Nyquist theorem bit rate agree with the intuitive bit rate described in the baseband transmission? They match when we have only two level. In the baseband transmission, the bit rate is 2 times the bandwidth. But in broadband transmission, we can assume that it can be more than 2. It can be 4, it can be 8. But if we use only the first harmonic in the worst case, however, the Nyquist theorem is more general than what we derived intuitively. It can be applied to a baseband transmission and modulation, and also it can be applied when we have 2 or more signals. Okay. So consider a noiseless channel with a bandwidth of 3000 Hertz. Bandwidth of 3000 Hertz. So for a Nyquist theorem, the formula should be bitrate is equals to 2 multiplied by bandwidth multiplied by log base 2 levels. How many level you are sending? So if we are putting the value from this question into this, so what will happen? 2 signal level, so it means L is equals to 2, bandwidth is 3, so this becomes bandwidth, and the maximum bitrate can be calculated how many bits you are transmitting through a channel by using Nyquist theorem. It means if there is no noise, noiseless channel, so 2 into bandwidth into log 2 level L. So it means 2 into 3000 into log 2, it means 6000 bps bits per second. It means through a channel you can transfer, you can deliver 6000 bps by using this noiseless channel, Nyquist theorem. Okay, another. Consider the same noiseless channel, a signal with 4 signal level. So it means log 4, so it means 12,000 bps. So it means just the double with the same transmission channel. So it means the same transmission channel, if we increase the level of signals, somehow we can reduce the reliability. But yes, there is a limit of the channel that you can send 6000 bps, 12,000 bps or 24,000 bps. There is a limit. If we beyond this limit, we are transferring the data beyond this limit, obviously we can lose the data, we can lose the reliability. Okay. So we need to send, take another example. We need to send a 265 kbps over a noiseless channel with bandwidth of 20 kilohertz. How many signal level do we need? We have 265 kbps. It means this is the bit rate 265 kbps. It means 265,000 bps is equal to 2. Bandwidth is 20,000, 20 kilohertz. This is bandwidth into log 2 L. So you need to identify the L. So L becomes 2 to the power 6.625. So this is not the power of 2 because we cannot calculate anything, the levels in the decimal, in the point. So either we can use 2 to the power 6 or 2 to the power 7. What do you think? You can use 2 to the power 6 or 2 to the power 7. If you think that the signal can accommodate more bandwidth, then obviously you can use 2 to the power 7. But you think by increasing the level, we can lose the reliability, then you can assume it 2 to the power 6. So it means either this can be 64 or 128. Either 64 or 128. So what is written over here? We need to either increase the number of level or reduce the. If we increase, we have 120 levels, the bit rate is 280. If we have 64 levels, the bit rate is 240 kbps. What is near about it? 280 kbps. But here is 265. So this is beyond the limit. So we cannot accept that we can increase the level. We can reduce the level also. So 240 over the 265 kbps, we can deliver the bit rate is 240 kbps and we can increase the reliability. So we can have 2 to the power 6. L is equals to 2 to the power 6. Okay. Take another example. Extremely noisy channel where noise is too high. So Nyquist theorem applies when noise is, there is no noise, noiseless channel. And if we are talking about the noisy channel, then Nyquist formula is not applied there. Shannon algorithm can be applied if we are using noisy channel. So what is Shannon algorithm? B log 2 1 plus SNR. This is the formula for Shannon algorithm. Okay. So if we are using extremely noisy channel where the noise to ratio is almost 0. In another word, the noise is so strong that the signal is faint. There is no signal. We are not assuming that what is original signal. We are not receiving the original signal. We are just receiving the noise only because the original power of signal has been lost somewhere. So the capacity of the signal can be calculated as by using Shannon algorithm. C is equals to B log 2 1 plus SNR. SNR becomes 0. So B log 2 1 is equals to 0. So what is this? Just a 0. The capacity of the channel is 0. So it means, in other words, we cannot receive any data through this channel if there is extremely noise is there. So we can calculate the theoretical highest bit rate of a regular telephone line if we are assuming that we are using telephone line. So telephone line normally has a bandwidth of 3000. The signal to noise ratio usually 3162. This is just approximation, not exactly. For this channel, we can calculate the capacity as by using Shannon formula. That C B log 2 1 plus SNR. So B is equal to bandwidth and this is the SNR. So what is this? 34,860 bits per second. So this is the average transmission speed of your telephone line. So the signal to noise ratio is often given in decibel also. If you can convert the SNR into SNR dB. So assume that SNR dB is equal to 36 and the channel bandwidth is 2 megahertz. the theoretical channel capacity can be calculated as SNR dB. This is the formula. SNR dB is equal to 10 log 10 SNR. Okay? SNR is equals to 10 SNR dB upon 10. So SNR is equal to 10 to the power 3.6 is equal to 3981. So you can calculate C as B log 2 1 plus SNR, which is equals to 24 Mbps. So SNR dB you can calculate. SNR dB is equal to 10 log 10 SNR, and the capacity of this channel is 24 Mbps. Okay. For the practical purpose, when SNR is too high, SNR is high, it means signal to noise ratio. It means signal power is too low and noise power is too high. So we can assume that SNR plus 1 is almost the same as SNR. SNR plus 1 is almost same as SNR. So in these cases, the theoretical channel capacity can be simplified into C is equal to B into SNR dB upon 3. For example, if we calculate the theoretical capacity of a previous example, we can calculate it also, which also gives 24 Mbps as it gives in the earlier example 24 Mbps. So, student, do not misunderstood that this is different or this is different. Both are same because we can assume that SNR is just equals to the SNR plus 1. SNR plus 1. So, we can apply this formula also. So, if we have a channel with a 1 megahertz bandwidth, the SNR for this channel is 63. What is the appropriate bit rate? Just put the formula. C is equal to B log 2 1 plus SNR. B is equal to 10 to the power 6 1 megahertz to 10 to the power 6 plus 63, which gives 6 Mbps. Very easy questions. And the Sharon formula gives 6 Mbps. Now, this Shannon formula gives 6 Mbps. Now, the upper limit, the better performance, we choose something lower 4 Mbps, for example. Then we use Nyquist formula to find the signal number of levels. How many levels of signal we can transfer through this channel. Listen carefully. There is a noisy environment or there is a noiseless environment, but practically there is no noiseless environment. Through a noisy environment, we can assume that if we are delivering something, the noise cannot impact on this my signal. So we can use Nyquist theorem also. So by using Shannon algorithm, noisy environment, we can assume that 6 Mbps is the bit rate, 6 Mbps, but there is some noise. Okay. So in 6 Mbps, maybe 1 Mbps is the noise and 5 Mbps is our data. This particular bandwidth can be used as this one. 10%, 20% of the noise is there and rest is the data. But if we think that this becomes a noiseless environment, noiseless channel, then we can use this formula. Shannon formula gives 6 Mbps, the upper limit. For better performance, we choose something lower than 4. So 4 Mbps, we can put 4 Mbps rather than 6 Mbps is equal to 2 into bandwidth into log 2 L. So L becomes 4. The 4 levels of a signal in a civil we can deliver through this channel in a noiseless environment. Okay. So Shannon capacity gives the upper limit, while Nyquist theorem tells us how many levels we can use for this particular thing. So this is all about the signaling, different types of attenuation. You have observed distortion and noise, and some numerical example using Shannon and Nyquist theorem. And thank you very much.